About introduction to quantum Hall effect.
Yes, I'm not sure how. Okay, I'm not sure how many of you need this introduction, so please feel free to interrupt or to speed up things if you want. So I'm going to talk about some introduction into fractional quantum Hall effect or quantum Hall effect in general, and then I hope to get to my work as well, which deals with geometric responses of quantum Hall systems, but I'll start with very elementary stuff. So Hall effect. So we have system where in a perpendicular magnetic field we send current in one direction and we measure the voltage across the transversal direction. We introduce the ratio of voltage to current and called it Hall resistivity, and simple classical balance between Lorentz force due to electric field EE and the electric field force and Lorentz force due to magnetic field EV over CB gives you estimate for this Rxy, which is just magnetic field divided by the concentration of electrons and E times C. E is electric charge of electrons, C is speed of light, and E is the number of electrons per unit area, B is magnetic field perpendicular to the sample. So in particular, if you plot the dependence Rxy as a function of magnetic field, just from this formula you see that you're supposed to get a straight line. And the slope of this straight line depends on the number of charge carriers, and this is how it was used in solid state physics up to recently, just to measure the charge carriers density. Okay, and also another important thing is that you can introduce also normal resistivity, which is the ratio of voltage along the current to the current. And typically it's determined by the impurity scattering, and it's just constant. It depends on magnetic field slightly, but not so much, so it's roughly constant classically. So this is a typical picture that you expect. So the question is what one should see if we now take all this to extreme. Let's take two-dimensional sample. So these are important things. So now we go to quantum Hall effect. So we take two-dimensional sample, which is usually just the surface of some semiconductor. And so using electric field, we bring electrons to the surface, and the motion is quantum mechanically two-dimensional. So this is two dimensions. Then we need very clean sample. So almost no impurities, very few impurities. And very low temperatures and very strong magnetic field. What is low, strong, we'll see a little bit later when I compare scales.
What is the effect of low temperature?
That doesn't spoil everything.
Is it making the electrons have less kinetic energy or something or other like that?
I'll discuss that. So when I compare, when physicists say low temperature, you need to know low compared to what. And in this particular case, it's low compared to the distance between Landau levels. I'll say a few words about that one in 1 minute, actually, very soon. So, but basically, we'll take this. In practical matters, B is of the order of 10 Tesla, which is like a very strong magnet. Low temperature means 1 Kelvin and below. And clean means the samples with the best mobility available at that time. And two dimensions is the surface of semiconductors specially prepared with impurities far away from the surface so that to make mobility nice. Okay. This experiment was done, and surprisingly, in 1980, the picture was totally different. Yes?
You said by clean you mean high mobility, does it mean that low disorder?
That's right. Low disorder, yes. As low as they could go at that time, actually. If you have strong disorder, you don't see anything. Okay, and then what happened is that instead of this straight line without features, the measured Rxy at low temperatures under this condition was consisting of various plateaus, And moreover, these plateaus happened are initially at exactly integer numbers of, so for example, this is h over e squared, and the next plateau was 1/2 h over e squared, then 1/3 h over e squared, and so on and so forth. So this is actually the actual picture that the experimental data. So just for you to get
The curves going between plateaus.
take a look. Basically, the lower temperatures, the cleaner sample, the sharper it works. Many of you saw this picture, of course, many times, but just to give you.
long and some short.
You mean plateaus or?
Plateaus. This is long plateau.
Right. We'll talk about all that. So, okay. So this was so instead of Rxy, people usually use sigma xy, the whole conductivity, which is roughly 1 over Rxy. Not quite, but for now it says. And this is e squared over h times n, and n originally was integer number 1, 2, 3, 4, and this is called integer quantum Hall effect. Integer quantum Hall effect. Okay, and these are these major plateaus. The biggest one, 1, and then a bit smaller 2, smaller 3, and so on and so forth. Okay, but then as a surprise, it came that actually the next plateau was observed at the value of 3h over e squared, which corresponds to coefficient here instead of n being 1/3. So we write generally e squared over h times nu, and nu can be also 1/3, 2/5, and fractional numbers. And this is called fractional quantum Hall effect. So on this picture, this is 1. Okay, this is the main plateau which they observed first. This is 3. This is 1/3. Okay, this is fractional, corresponding to 3h over e squared. And 2, 3, 4 is this series of plateaus. They're shown here, 2, 3, 4. Okay. So also interestingly, if you look at Rxx, which is the regular resistivity along the current, then this resistivity has minima everywhere. Every time you have plateau, it goes to 0. So it wildly oscillates. This is this lower picture.
This very oscillating thing here.
This is what I'm talking about right now. So,
What do you think?
so there are two plots on the same graph. One is Rxy, which is just this step-like thing. Another is Rxx, which is the longitudinal resistivity along the current, the regular one, voltage. And this is oscillating wildly, and more importantly, it's 0 every time you have plateau in Rxy, almost 0.
Conductor on the plateau.
It's not superconductor. It's a kind of opposite. It's not conducting at all.
I mean, yeah.
Okay.
Well, resistivity is 0.
Okay. This is some resistivity trigger. So J equals sigma E. This is the J is the current density, E is electric field, sigma is the definition of conductivity. So if you have two directions, then we usually write it as a matrix: sigma xx, sigma xy, sigma yx, sigma yy times ex ey. Okay. So if you apply electric field, then current is x direction is linear superposition of field in x direction and y direction. Well, for isotropic systems, sigma xx and sigma yy is the same, so this is the same number. And sigma xy is sigma yx with minus sign, so I can just put here minus. So resistivity is, you have to invert this 2x2 matrix, okay? And when you invert this 2x2 matrix, you get sigma xx squared plus sigma xy squared from determinant. And then you have sigma xx minus sigma xy, etc. So in particular, Rxy is minus sigma xy divided by some sigma xx squared plus sigma xy squared. And Rxx is sigma xx divided by sigma xx squared plus sigma xy squared. Okay, here unusual thing which is important to understand that when sigma xx equals 0, Rxx is also is 0. Yeah. So you might think that if it's ideal conductor, then 1 over this will be infinitely resistive. No, it's because in the presence of transverse thing, it's different story. So when I see here that sigma Rxy is finite and Rxx is 0, it means that sigma xx is also 0. So it actually is an insulator. It's not conducting here at all. Okay.
To read that, is that RYY?
Okay.
X,
this is xy.
That's xy.
Xx. So I basically invert this matrix.
That's xx. Okay, and then the numerator on that xy, the Rxy. What's the numerator on the right side?
This one?
Yes.
Sigma xy. And sigma xx. So if sigma xy is equal to 0, then you have regular formula that Rxx equals 1 divided by sigma xx. This is where our intuition is coming from. But when it's not 0, then it's a little bit different. Okay. Okay. So first of all,
Can I ask you a question?
yes, sure.
The fractional quantum Hall type is seen in exactly the same physical objects that the integer one was seen in. It's not an. It's
Absolutely. They just made it cleaner and increased magnetic field more, and they saw a new plateau. Yeah. This was quite. I mean, experimentalists would hate me for saying that because for them this was really tremendous step. They really improved quality of materials quite a lot to go from integer to fractional. But for us, it's just the same two-dimensional gas, just different magnetic field. Okay. Just some trivial exercise is to take the formula for sigma xy, which is observed, which is E squared over h times nu, which is observed on plateaus. So on plateaus, this is the formula, right? So nu equals 1, 2, 3, 4 is integer Hall effect, and nu equals 1/3 is, for example, fractional. And just compare it with classical, totally classical formula, EC over B times ME. Okay. So this is classical prediction. This is just drift velocity of electrons in crossed electric and magnetic field, knowing from undergrad electricity and magnetism, multiplied by the density of electrons to get current. So this is really trivial, simple formula. And this is what we actually, where we actually observe plateau. Okay. So, and in particular, we can take a look at what is nu here. Just solve for nu, which is 2 pi h bar divided by E squared. I replace h by 2 pi h bar times E C over B and E. Okay. And then 1e cancels, and hc over eb has dimension of length squared. hc over eb has dimension of length squared, and it's called magnetic length. Lb is magnetic length. So what I see is that nu is 2 pi Lb squared multiplied by Ne, or Ne divided by 1 over 2 pi Lb squared. So the nu is the ratio of how many electrons I have to some typical scale for the density of electrons, which turns out to be the density of electrons on the first Landau level. I'll come to that in a second. So therefore, we call this nu filling fraction. So if it's multiple of this, we call it integer Hall effect plateau. If it's fraction, we call it fractional Hall effect. Okay. Another way to rewrite it is we multiply it by the density by the total area, and then it turns out that we get the following: we get the total number of electrons in the whole sample divided by the total flux of magnetic field. So I multiply here numerator and denominator by area. Here I'll get total number of electrons. B multiplied by area is total magnetic flux. And this HCE forms this way, HC divided by E, which is called flux quantum. So this is the quantum value of flux of magnetic field. The same one which occurs in superconducting vortices, the same combination. So what I can say is this nu is the number of electrons divided by the total flux of magnetic field expressed in terms of the number of flux quanta. So in both cases, I see that quantum scale shows up. This length has h bar in it, so it's definitely quantum physics. And here it's flux quantum appears, which also has h in it. So it's quantum physics. So the idea is that, of course, this is quantum phenomenon, and you should be explaining it with quantum mechanics. So what are important factors here? It's 2 dimensions, very clean sample, strong magnetic field. Important features are plateaus, the fact that it's actually not going monotonically, but it stays the same for some range of the values of B. Very precise quantization. So the accuracy with which this is actually 1, not 1.1. The accuracy here is 10 to the minus 7 in original experiments, and now it's 10 to the minus 9 or so. So it's 1 in a billion accuracy. Actually, this now is used as a standard for resistivity instead of original.
How about the width of the plateaus?
And then another thing is the gap in the spectrum. So because this sigma xx is 0, so it's not conducting, it seems that when we usually have non-conducting systems, for example, an insulator, when our low energy levels are filled, then there is a gap in the spectrum of the microscopic Hamiltonian, and then there is a conduction band. So if I have electrons here, then it's conductor. If I don't have electrons here, and there is a gap separating the ground state from excited states, it's insulator. So the fact that it's not conducting here means that there is some energy gap in the system, which is not surprising at all when you have this change between 1 and 2, because we will show that Landau levels are easy to explain. But it's more surprising when you have 1/3 and still plateau. So basically, the idea here is that the width is determined roughly by the size of this gap. So the bigger this gap, the bigger the width of the plateau. Okay. But I'll say a few more things. It depends on many things. It basically depends on impurities on many things. But roughly, the plateaus can be hierarchically ordered. The biggest one is the plateau at 1. The strongest, the most robust one, the one which shows first, which has the biggest gap, and then the rest are not so good. Okay. Sure.
So if it's perfectly clean, no impurities,
Right.
the steps disappear.
That's right.
Now, if you had a tiny amount of impurities, then they appear, and then you increase the impurities, they disappear again.
That's right.
Right?
Right.
What is this transition from as you increase disorder? Is it described?
The problem is that this picture that you describe, you have to remember about limits. We have microscopic samples. So if ideally I would have infinite plane in which I measure, and very, very small as you can, but finite density of impurities, then I would have, instead of this, I would have picture like perfect picture like this with really good steps. And this transition is very sharp. But then if you add more and more impurities, this becomes, or temperatures, this becomes more and more smeared. Okay, and if it's really big, then it will just smear the whole thing. But it's important. You might think that the way to go to limit is what you actually want is to remove impurities from the sample totally, which is, I'm saying that I'm in different limit. My limit first is sample goes to infinity, and then the number of concentration of impurities goes to 0. Then it's okay. Then you always see that, and the less impurities, the better. But of course, if sample is finite, then when you remove all impurities, it will be just free ballistic motion of everything and no plateaus in that case. Okay. Okay, microscopic Hamiltonian. I just say a few words about that and just to compare scales. But basically, it is believed that this Hamiltonian written here will potentially capture all this intricacy of Hall effect. Oh, this is very theoretical statement because nobody knows how we actually treat it. What is this Hamiltonian? These are two-dimensional electrons in the presence of constant magnetic field. So curl A here is just constant B. This is Coulomb interaction between electrons. Well, epsilon is dielectric constant of material, but what are Coulomb interaction? Then impurities. This is random external potential. You can also include here some regular external potential, for example, potential due to the sizes of the sample, confining potential. And this is something to do with spins of electrons. Okay.
The last one.
Say it again?
The last one is important.
For some of the effects, important. Not for us today. So the scales are the following, that the energy scales here is h bar times omega c. Omega c is classical quantity EB divided by mc. This is cyclotron frequency. Well, instead of m here, you have to take m, which is the bent mass of electrons, the effective mass of electron moving in semiconductor. But other than that, it's just simply standard classical quantity times h bar. This is the distance between Landau levels in the spectrum of single particle. So this is a typical scale of kinetic energy, the separation between levels. This is Coulomb scale. The typical one for the filling factors of the order of 1, it's E squared divided by epsilon, and typical distance between particles is magnetic length, LB. So this is the typical Coulomb energy. Well, this is some delta U depending on how many impurities you have and so on and so forth. And this thing is the Zeeman splitting. And basically what I'm going to say is that for us, we will assume the following, that the biggest scale is this kinetic scale, h bar omega c. The next one is Coulomb. And then there is this Zeeman splitting, temperature, and impurities. Okay.
Which one in the middle is?
Vc is Coulomb scale. Just Coulomb repulsion of electrons. Okay. In reality, for some typical numbers, this h bar omega c is 20 times b. The answer is in Kelvin if you express magnetic field in Tesla. Okay. So for 10 Tesla, for example, it's 200 Kelvin. So I measure this separation in Kelvin. And Coulomb energy is something like 50 square root of B. And for 10, it's like 350 Kelvin. Okay. And this stuff, I mean, this is of the order of 1 Kelvin, and the same here. Yeah.
When you're imagining your, what do you call it, a sample?
Right.
Do you imagine it to be the whole infinite plane, or is it like some region in the plane?
For most of the purposes, I imagine it's the whole plane. Sometimes you want to really look at the sample, which is this whole bar geometry, because this is how you make contacts. So you're interested in what happens on the boundary, actually.
Or is that a finite thing?
Typically, they actually can manufacture quite different geometries, because it's not that they just have to really cut sample in a particular way, but what they have is they have surface, and they can, for example, apply some positive voltage here of arbitrary shape, and this will form your whole droplet right underneath. So you can study boundary of this droplet. So you can make several things. You can make multiply connected geometry, and you can make many things. But mostly, you are saying that to study what's going on in the bulk, in the middle of this whole droplet, I consider just infinite plane. If I want in particular to look what's going on the boundaries, then I will consider like half plane or disk or whatever I want.
So what do you imagine U to be like, this potential?
The random potential?
Yeah, what kind of a potential is it?
Or for example, one of the models is just to have delta correlated potential.
I mean, how does it does it grow at some rate at infinity?
No. It's just like random stuff, which is this is typically what happens is this is just impurities. So to dope semiconductor, you really have to put some materials which give electron to the surface, but then they have positive ions. So these are basically just scattering centers. It's like small positive bumps.
Something about if you said that if the impurities was 0, you would just have ballistic motion of electrons. Right. So I don't understand that, because the electrons, first of all, are influenced by the magnetic field, and secondly, they have Coulomb repulsion.
Well, let me explain. This is really simple to explain. So suppose that I have magnetic field here, and I apply electric field, say, in this direction. And suppose that I don't have impurities, so this is just plain. So what I will do is I will go to the reference frame which moves with velocity E divided by B times C in perpendicular direction. In that reference frame moving there is no electric field. It's just Maxwell equations, so it's transformations. So in that reference plane will be no electric field, so on just magnetic field, so I don't have current. Therefore, if I go back, I just see that all electrons move with velocity b. They actually rotate, make circular motion, but as a whole thing, they move with this velocity v. This is where my classical value comes from. I just multiply by the concentration, and then I read this as a whole conductivity. So that's the calculation which I hinted on in the beginning. Okay. They are repelling each other, but this doesn't affect argument at all.
You mean the whole group of electrons is?
Yeah, the whole thing moves with a constant velocity, which is given by this simple formula. They repel each other. If you think about what's going on when they repel each other, think about this. So these are two electrons, they repel each other, so there is this force. They start to accelerate, okay? But then magnetic field turns them. So as a result, if you think how it will work, they will just be rotating like this.
Right.
And they will not move anywhere, so they will not create current. Okay. So you might think that I should really not see any plateaus at all. So what does this argument break? But of course, if I have impurities, then even if I go to that reference frame, I will have no electric field, but I will have moving impurities which will push electrons. So this argument breaks right away when I don't have any translational invariance anymore. Therefore, clean system is sort of very special limit. So you have to be careful with that. Okay.
What about if you have say a disk?
Right.
Can you does it is much different the situation from the what you for example the sharpness of the plateau, can it be?
Disk is used. I don't think that it matters for anything of that type for the sharpness. I know that they use disk quite a lot. This is called Carbina geometry in experiments, and the reason is basically that it's very symmetric. So they usually send current radially and then measure electric field perpendicular or actually, sorry, apply voltage here, and then current will circulate, and they can measure it using magnetic field measurements. So they use it. This is all due to the local physics, so it should not be that important. But okay. So the reason I showed this Hamiltonian and these scales is that basically that the strategy will be first think that this scale is huge and solve the problem of clean system and electrons in magnetic field on the plane. Then think what happens if I introduce Coulomb interaction between electrons or some other interaction, and also impurities, temperature, and everything else. Notice that experimentally, this is like 200 Kelvin, this is like 150 Kelvin. So it's not so that it's much bigger than this. So
where does the temperature go into the Hamiltonian?
Temperature does not go into Hamiltonian, but temperature goes in the distribution function. If you have spectrum, for example, you have one completely filled Landau level. At 0 temperature, this will be it. This will be just a filled Landau level. But if you increase temperature, then there will be some electrons which will be sitting in the upper energy levels with the probability e to the minus h bar omega c divided by temperature. Okay. So you will always have excited electrons here and holes here, and then you have to consider this a more complicated system. So even if you have filling factor 1, it's not actually 1, but it's it's corrected by temperature, and that's what smears the transitions from plateau to plateau. Okay. Okay, now I'll go quickly over solving one particle problem in magnetic field. So Landau levels. Okay, so Hamiltonian is 1 over 2m. I will write it first in all glory with all numbers. And A I will take to be 1/2 B times R, such that curl A is B times Z hat. So perpendicular to the plane. This is particular gauge. And I will introduce, of course, Z equals X plus I, Y, and complex conjugated complex coordinate of electron. And D equals 1/2 dx minus I dy. These are notations. Then it turns out that Hamiltonian can be written as H bar omega C times A dagger A plus 1/2, where A is 1 over square root of 2d bar plus 1/2 Z, and A dagger is Hermitian conjugate. Okay. You can also introduce the combination B, operator B, which is 1 over square root of 2d plus 1/2 Z bar. Okay, this is 2. No, the conjugate A dagger is 1 over square root of 2 minus 2d plus 1/2 Z bar. Remember, then I will do Hermitian conjugates, then the operator dx goes to minus dx. So these are Hermitian conjugate with each other, and they have.
Hermitian conjugate, you're looking at the e to the minus mod z square measure on.
No. Just okay. Just take this as a definition.
Hilbert space.
I understand. But okay, let's just look at this. These are definitions.
It is the Bergman-Fock space, right? It's a Hilbert space of entire holomorphic functions.
Right.
And with the measure e to the.
No, absolutely, yes. What I mean is this: that I have. This is my scalar product, d2z. I do not want to separate it into Gaussian part and holomorphic part yet.
You're taking holomorphic function times the Gaussian.
Times the complex conjugate, yeah. Yeah, this psi is the whole thing. It's holomorphic times the Gaussian. And if you define it with respect to this Hilbert, this scalar product, you get this expression.
Okay.
Okay. Important thing here is that A dagger is 1.
The lowest on the level field, you also need to consider the holomorphic functions.
Right. I did not specify yet to the first Landau level. That's
You also need to consider what?
Anti-holomorphic.
Anti-holomorphic.
yeah.
This
Don't you look at the.
I'll say.
H?
Let me say. I'll come to that. Don't digress. Okay. So A dagger is equal to 1. So you can easily check that. You can also check that B dagger is 1, and you can also check that A commute with B dagger. So these guys commute with each other. Okay. So you can construct state, which is. You can construct state 0, 0 such that A and B annihilate the state. Okay, and you can write explicitly the wave function corresponding to this state, which is 1 over square root of 2 pi e to the minus absolute value z squared over 4. From now on, I measure distance in units of magnetic length. So magnetic length is 1. If not, then you put here LB squared, because in exponent you should have dimensionless quantity. Okay, so this is my 0, 0 state. And then, of course, you can make a dagger to the power n, b dagger to the power n, say, plus m, times 0, 0, and that will give you state nm. Okay?
It's going to be z to the n, z bar to the n.
Almost, but not quite. I'll write it. So the Hamiltonian times nm gives you En times Nm. This Nm is eigenstate, and En is just h bar omega c times n plus 1/2. And the energy does not depend on m. Okay. So example, if you take n equals 0 m, then explicitly this is 1 over 2 pi 2 to the m factorial z to the m e to the minus absolute value z squared over 4. Okay. If you want general, then nm, it's something like this. E to the z bar over 4, dz bar to power m, dz to the power n, e to the minus z bar over 4. And I think it's like this. Yeah. So it's almost like this, but not quite. It's because this a and b have derivative nz, so it's a little bit more complicated. But you can write it easily. So what's important is that for zeros Landau level, these are all holomorphic functions. And so far m equals 0, 1, 2, and up to infinity, no restrictions. So in fact, because the energy is totally the same, I can take any linear superposition of this function. So any function of the type of holomorphic function of z e to the minus z bar over 4 also belongs to the lowest Landau level. Okay. To characterize state, you need two numbers, n and m. So one number, n, is the eigenvalue of Hamiltonian. Another number is eigenvalue of the angular momentum operator, which can be written as b dagger b minus a dagger a. So L acting on m, and m gives you m and m. And this L is obtained from minus I d over d theta, where theta is the azimuthal angle in the plane. You have to be a little bit more careful here because the values m takes are from minus n to minus n plus 1 and 0, 1, and up to infinity. Okay. So I describe spectrum and wave functions. To infinity. No, this is oscillators. This is not a spin operator, so there is no restriction from above. It just goes to infinity. In fact, this is a very simple picture. Shows how it looks like. For this, you just have to take this psi, for example, at zeroth level, 0m, absolute value squared. You can immediately see that it's proportional to radius to the power 2m, e to the minus radius squared divided by 2. And you can just find where the maximum of this is. And you'll find that the maximum is the distance square root of 2m from the origin. Okay. So basically it looks like this. The first function is some blob inside, and then there are like strips which go like that. And each of those each of those circular strips has area of 2 pi lb squared. Okay. And this is why if you say that your disk, you have finite disk, then you try to fill it, and then at some point the boundary will be encountered, so you don't want to go beyond that, so you stop. And this will be a finite number, and you just ask what this number is, and this is just the area of the disk divided by the total number of flux quanta, or total area divided by 2 pi lb squared. So this is the capacity of Landau level. Okay. So far this is all single electron physics in magnetic field. So let's try to solve first many body problem, but it's not actually many body. Let's see what's the wave function of the completely filled Landau level. So what I'm interested in the wave function phi1 of z1 zn, which is completely filled Landau level. Well, I'm saying that let me start with the states are 1, z1, z1 squared, z1 to the power n minus 1. This would be the total basis of states for one particle. And now I'll just do the same, but for the second particle. And then I take determinant of this and multiply by e to the minus sum zi squared over 4. And of course, this is van der Monde determinant, so it can be written as I minus j, zi minus zj. So phi1 is given by the product up to normalization zi minus zj e to the minus zi squared over 4. Okay, that's standard formula. Interestingly, what is two-field Landau levels? How does it look like? So you need to include non-holomorphic functions, because already next level includes z bar to the power 1. And it turns out that actually you can do this. Let me use the advantage of the blackboard. So what I will do is I will erase it and do this. I will put here n over 2. So this is all my electrons filling the first Landau level. But then I will write z1 bar, z1 bar, z1, z1 bar, z1 to the power n over 2 minus 1, and so on and so forth. And this is determined. This is still square matrix if you count carefully. Okay. So this is the wave function of two completely filled Landau levels. I bet none of you have seen this before, because this is very rarely used. Huh?
This is not van der Monde.
This is not van der Monde, but it's still slated determinant. It's slated it's determinant because it's non-interacting problem. So I'm dealing with a non-interacting fermions. So, but this
And
is a different formula.
how does it look like in this product?
I don't know.
Ah.
I'm not sure.
How do you think, so in terms of the electrons, what are the Z1 bars? I mean, when you have anti-holomorphic things, how do you think about what that is? You said this is two filled Landau levels.
Right.
What picture do you have in your mind about the n electrons is going on here? I mean, when you have a Z,
Yeah, I think I understand. So, if you look at this, what you see is that from the radial point of view, it's just basically radius to the power n over 2, right? So it's the same as before, so it's nothing new. But this radius is not matched by angular momentum. So basically, if you put on the second Landau level electron with the same shape of the density support, then it moves not so fast. Or actually, it moves faster, I think, than the lowest one. Moves faster is not a good idea, but
somewhat spatially, you sort of fill up your disk, I think, right?
Right.
With electrons, and that's your first filled Landau level.
That's right, yeah.
Right, and then you want to do another layer.
And you just put it on top, but to make them orthogonal, you make a different angular dependence. That's
Okay.
so they at the same point in space. So they're not splitting space, real space. They're on the same point, but just have different generalized momentum, so that they are orthogonal to each other. There is another way of thinking about this semi-classical. If you think about classical electron, which rotates cyclotron orbits with frequency omega c, this is what, if you just kick charged particles, that this is what it does, and it can do it over the radius of any size. Just kick it stronger, it will be bigger circle with the same frequency though. So there is really huge constructive interference. But then you ask what happens in quantum mechanics. Well, in quantum mechanics, the area of this should be multiple of so that the total phase is 2 pi times something. So basically, the first Landau level in that when this flux is precisely 2 pi, and when the phase is exactly 2 pi, and the next Landau level in the phase of 4 pi, and so on and so forth. That's a semi-classical picture.
Yeah.
Okay.
But I mean, because you put n over 2 in the exponent,
right?
You sort of like, you have half of them as z's and half of them as z bars somehow.
Right.
You put some new angular momentum or something into the lower half, right?
Right.
You think of them as just like layers of electrons, though? Or no, you're thinking of them actually at the same point?
Yeah, they actually at the same point.
You just change the state, the sort of the type of electron or the state of the electron at each point? No.
Well, I mean, if you have just circle, if you put one particle in a circle, so suppose that this angle is phi, let me put particle with a wave function e to the I phi. It just moves here like this, and it's on a circle. I can take the same circle and put function with wave function e to the 2 I phi on the same circle. They are on the same circle. Moreover, their density looks exactly the same. It's just constant. But they have different angular momentum, so they are orthogonal to each other. So it's not a problem from fermionic point of view. So that's. So they actually are the same. In fact, electrons on the second Landau level, as you can see, very similar to the first one. Therefore, we usually, for quantum Hall purposes, we usually just say, okay, if I have filling 5 halves, the first 2 Landau levels are filled. Let me throw them away and think about this levels filling 1 half. So it's kind of similar to the very lowest Landau level filling by 1 half. And I just consider 1 Landau level filled. This is not quite good because matrix element of those impurity potentials are different. So it's a little bit different on upper Landau levels. But roughly from the point of view of this general analysis, it's indeed very similar. Okay. And with the speed I'm going, okay. Okay, what is the spectrum? The spectrum is this Landau levels at h bar omega c over 2, 3 halves, h bar omega c, and so on and so forth. The distance between them, h bar omega c. Now, what happens if I add impure? Okay, what happens if I have partial filling? So what we saw is that the integer Hall plateau occur when I fill my system up to this point. This is plateau number 1. We did it experimentally by changing magnetic field, but it's the same as changing distance, so it's basically the same story. It's just, you can think of it as just changing the number of electrons. I fill 1 Landau level, I have that big nice plateau with n equals 1. I fill 2, I have smaller plateau with n equals 2, and so on and so forth. And if I fill exactly 1, then the formula, the classical formula for Hall conductivity gives me precisely correct result. The problem is why plateau? So why is it not changing? For this, you have to understand what happens if I partially fill this level. Suppose that
I'm not.
Yeah.
I'm sorry, I'm just not quite understanding the term fill.
Okay.
What do you mean by? I mean, you have like a disk, for example.
Right.
And you want to put a number of electrons in, and so you end up with the first n wave functions or something like that, right?
Right.
Because you're okay.
So yeah.
Then what does it mean to put another layer on? I mean, I still don't quite understand. I mean, you want to fill another. Do you say fill another?
I'm not even talking about this. Let me say this. You have a disk.
Yeah.
Let me fix magnetic field, so not to change several things simultaneously. I fix magnetic field. There's a particular number n of states which on Landau level, which I can put on this disk.
Yeah.
Okay, so this n equals the area divided by 2 pi L squared. This is some particular number. If I put exactly that many electrons, I will have my first Landau level completely filled. In the sense that if I want to put one more electron, I have to put it in the upper level. If I want to remove it, I can remove it from here. If I want to put extra, I have to put here. Okay. So this is a spectrum, but it's very degenerate spectrum. Each level here has that many states.
Let me just see if I'm getting the
Yeah.
language correct. You put n electrons in the lowest Landau level
Right.
of the disk. Now you want to put another electron in?
Right.
And so it has to be an excited electron.
Exactly. Yes.
Just by the Fermi thing, because you can't.
Absolutely. I can.
Exclusion principle. It has to
Correct.
be an excited one.
Right. So it cannot go here.
Allowed to put an excited electron in that thing? Like how many electrons can you? I mean, how many? Is there like a limit? No. Is there a limit?
Okay,
How many
Steve. Let me do it. Let me do it even differently so that it's closer to experiment. Let me suppose that there is one field on the level. Let me decrease magnetic field a little bit. Then the number of states is proportional to magnetic field on Landau level. If I decrease it, it has smaller capacity. So you cannot fit them all. So some of them you have to transfer up there. Okay. Nothing you can do. You just change magnetic field and you have to change filling of Landau levels. Or I increase.
Put any number of electrons on that disk. It's just that you have to keep on changing. Putting in a higher energy levels in order.
Right. You have infinitely unbounded from above spectrum.
Okay.
You just put electrons. Okay. So now remember this plot. This plateaus. So this is where I am when I filled exactly one Landau level. Right in the middle of plateau with n equals 1. Okay. Now question is, if I want to add more electrons or I want to change magnetic field a little bit, what will happen? For this I have to really understand how do I fill Landau level partially. Because basically it's hugely degenerate, so I can fill it in many ways, so what actually happens? And there are several ways to remove this degeneracy to figure out what happens. One of them is just external potential U of x. Just regular, not impurities, just harmonic potential. You can try and do this exercise in this symmetric gauge. You add to Hamiltonian potential, which is x squared over 2, which is harmonic potential, r squared over 2, absolute value of z squared over 2, like this potential. You can solve problems still exactly. You will see that actually the degeneracy of Landau level will change. Essentially what will happen is that in addition to a dagger a, to Hamiltonian there will be added b dagger b with some coefficient, which is proportional to this coefficient of harmonic potential. So degeneracy will change and you will have non-degenerate spectrums, then you will know precisely how to fill it with a given number of electrons if you want. That's one way, but this is not what's practically interesting. Practically interesting is to have U random. So you have impurities. What happens with impurities? With impurities, what happens is that this level is spread. It becomes, it has finite width. The way to understand it is very simple. If you have Landau level and you add impurity, for example.
Of the degenerate eigenvalue.
Right. So
you're going to split it up into a bunch of different eigenvalues.
Right. It's actually it's somewhat more tricky because, for example, if you put point-like impurity, really point-like delta function, so what happens is that there is a hugely degenerate level, and will be exactly one level will split off this, and will be having different energy. So it will not completely remove degeneracy, but it will just split one level. But if you have many impurities of various strengths, then still it will spread. So degeneracy will be lifted. Then you know what it means to fill it partially. You just, for example, say my chemical potential here, I fill it. So then this is my partial filling. Okay. The point is that, and this is much more complicated story, but the point is that these states which are actually I have some simple picture, but I don't have time for that. Maybe in question. So, point is that the states which are here in the tails of this impurity, they are localized. Okay. So basically, we have potential, and electron just goes around this center of potential, so it does not propagate. So it doesn't carry electric current. And sort of because of that, when my chemical potential, when my number of field electrons moves between middles of Landau levels, like here, then I add electrons, but they do not conduct, so resistivity stays the same. This is very crude picture, because you have to ask also yourself, or if you think about it more, why other electrons start to move faster to carry this excess of. Anyway, so it's cheating. It's cheating. So this argument explains qualitatively what's going on, but doesn't explain why quantization is so precise and exact. And for this, you need topological arguments of different types. But it roughly explains you what's going on. So when you go in the middle of Landau levels, this middle state is delocalized. It can go from one part of the sum to the other. When you chemical potential, when the level up to which you feel crosses this level, the conductivity jumps. Okay.
Localization of
Absolutely.
Random Schrodinger operator to explain this effect.
Right. Otherwise, you just don't see plateaus.
You know these sort of mathematical explanations like Belisar and some sort of topological things. There's sort of topological explanations.
Yeah, that's what I referred. It's the very first explanation of this type is 1981 by Laughlin, who invented topological argument explaining why this is so precise. So that it's
explanation's very non-topological.
This is not topological, right? This is roughly explains what's going on, like microscopically what's actually happening, but it does not. My argument definitely does not explain why it's so precise. I can do a little bit better using other pictures, but the actual precision of 10 to the minus 7 for this, you really need some type of topology or some more robust explanation. Okay.
What's the parameter responsible to define the structure?
For this one, this is the strength of impurities. The distribution.
It's not in the Laughlin states.
No. Laughlin states that.
They don't know about it.
No. No, this is totally okay. So far, I'm talking about integer Hall effect. Okay. Now, so this is the external potential, easy. The random impurities more difficult. There is very special techniques, supersymmetric sigma models, and all that type of stuff developed specially for that. Belisar is trying to use non-commutative geometry for this. So it's complicated story relatively. But then the question is, what happens with n equals 1/3? Well, with nu equals 1/3. Remember, there was a big nice plateau at nu equals 1/3, which means that 1/3 of Landau level is filled. And also, Rxx was 0 at this point, which means that there should be some energy gap there. Okay? And here, and remember also, my scales are that the Coulomb interaction is much stronger than impurities. So the right way to proceed is the following, that when I have exactly one Landau level field, I sort of can forget about Coulomb interactions if it's much smaller than this. Because the state is already fixed, so Coulomb interactions just changes the energy, but it's so rigid, so it cannot do anything. Okay. However, if it's filled partially, then I first should solve Coulomb problem and then impurities, because Coulomb interactions are much stronger than typically what impurities are. So the question occurs is what I should do if I have partially filled Landau level, strong Coulomb interactions, and let me assume that this h bar omega c is huge, so I don't really care about transitions between Landau levels and about other Landau levels. So everything is within one Landau level.
Why isn't this argument of logical if you do the calculation for no disorder?
Right.
You get integer numbers there. Right? For conductivity.
Okay.
So whenever you introduce disorder, you're basically adiabatically changing your parameter. And if there's no discontinuity, I mean, if I don't basically make the gap disappear, So this function, this perturbation is kind of continuous, and then I still have robustness.
Cool. I understand.
Do you understand what I'm trying to say?
But you do not change the number of electrons. No, I mean, what you are saying is applicable to this. Suppose that I have one exactly filled Landau level.
Yes.
And suppose it's clean system, so the whole conductivity is 1. Fine. Now let me take impurity from far away and bring it here.
I see.
Slowly. Then it's not changing. That's fine. But then you explain just why exactly this point is exact. Right? This point, which is precisely one filled Landau level. Or this point, is probably this point. But now, why it's not like this? This point is exact, but it's a little bit changing. For this, you have not only bring impurity, but remove electron, and then it's not. You will not be able to argue that simply. Let me move on. So let me move on, just because I probably have to wrap up and postpone the most interesting parts. But let me at least construct Laughlin's state, okay, if you don't mind. So what time I should finish?
We're flexible.
Finish the argument. Well, okay. First small comment is that remember that any analytic function will do. So one particular example, which is quite useful, is this: 1/2 eta. Eta is some parameter z bar, z, minus 1/4 z squared, minus 1/4 eta squared. This wave function also belongs to the first Landau level, because it's basically to the minus quarter, and then some analytic function, which is exponent. Well, if you look at the psi eta squared, you will see that this function is nothing but e to the minus 1/2 z minus eta squared. So it's like Gaussian, but localized around different points. So this is just examples of how many things you can do with Landau levels having huge degeneracy. You can actually move this Gaussian anyway. Right. Right.
They call it coherent state, right?
Yeah, that's precisely right. Yeah, that's the coherent state. Okay. So this is just example of how you can deform Laughlin's wave. It's important if you want to describe the droplet of arbitrary shape. Then you basically start with some other wave function, not the localized at the center, some arbitrary shape, and then you find others by finding orthogonal wave functions, and you fill first n, and then you'll have droplet of arbitrary shape. It's a useful trick. Okay, then Laughlin's state. Wave function. So what Laughlin wants to do is, he thought about trying to write the wave function of the ground state at the filling 1/3. Okay. So I have 3 more spaces for electrons than electrons. So what he wanted is to say that, first of all, this wave function should be built from the lowest Landau level wave functions. So basically, whatever wave function, many body wave functions I write, it should have e to the minus 1/4 zi squared, and some function here which is analytic in all variables. So this n-body wave function should be analytic in z1, z2, zn, in all of them, times this Gaussian factor. That's the first requirement. Second requirement is that system is rotationally invariant. I'm trying to build the totally rotational invariant wave function. So it must be eigenstate or eigenfunction of the momentum operator, which is equal to sum of I zi d over dzi. Okay. This is this d over d theta, where theta is angle. Okay. So what this means is that should be homogeneous function, right? So this is just summing all power, so it should be a homogeneous function. And, well, one way to write it would be zi minus zj, I minus j, to some power e to the minus sum of I zi squared over 4. Another good thing would be to have the wave function vanishing when particles come together, because this decreases Coulomb energy of particles. And the more they vanish when they come together, the better, because it means that they are on average farther apart from each other. And then one more requirement, and that should be antisymmetric with respect to interchange of these, because it's a fermions. So what this does is basically tells you that this should be some odd power.
What is the rationale for being eigenstates at Bell?
System is rotationally invariant.
You mean you're on a disk or something, or you're on a whole plane, or?
I'm on a whole. Well, let me say that I'm on a disk, or I'm on a whole plane, but I'm pickup center. In my gauge is explicitly symmetric around the origin. So I want my function to be also symmetric about it.
What makes the origin something? What's the origin mean in a physical problem?
This is a property of the gauge. What in this problem, what you should do is when you talk about rotational symmetry, you should use magnetic rotation. So which basically have to rotate your system and accompanied by gauge transformation, and study how things transform under this. But it's much simpler in this case just to choose particular gauge which is symmetric around the origin, and let me make everything explicitly symmetric around the origin. And that's what this argument is saying. So
can you say a little bit more why it's maximal power of the minus 2? Because it can be also.
I didn't say what's maximal.
You can take.
So far I just put arbitrary power.
But you can also have a function of the I plus the j. Homogeneous.
He wants it to be symmetric.
Oh, okay.
It's okay.
So basically, I have angular momentum. So every power is angular momentum.
Maximal.
Everything which I will add will increase the size of the whole thing.
Yeah.
So I really want to put them as for a given number of electrons in a volume, I want to put electrons as far from each other pairwise as possible. So I want to use all powers to make this zero.
Why do you want to do that?
Because they're cool. Okay, remember that I have psi of z1, zn, and then I have 1 over z1 minus z2. This is Coulomb interaction. I want to minimize this matrix element to make energy small. So therefore I want to have 0 as big as big.
Now I understand his question, but I don't understand the answer. So he was saying, you could, instead of raising the Vandermonde to an odd power, you could have taken the Vandermonde and multiplied by a symmetric polynomial, which was homogeneous. So your question was, why did you decide to raise the Vandermonde? I mean, it's sort of like trying to explain the desirable aspects of the Laughlin thing.
Right.
So you're trying to make it a ground state for something, right?
For the Hamiltonian.
Yeah, I have Hamiltonian with strong repulsion between electrons.
Initially, remember?
Yes, right.
Yeah.
So I mean, the energy
Take two particles. Let me take z1 minus z2 and
Power is
squared, and I have two choices: z1 minus z2 times this, right? Or I have times this, or I have z1 plus z2 squared times this. Okay, two choices of the same angular momentum. So of course I will prefer that because this
means that it's minimizing some energy.
Minimizing this. This is not rigorous statement. That's why I'm saying prefer instead of I can prove. But basically I want to minimize Coulomb repulsion of these particles. But for this particular case, you obviously can compare. I'm pretty sure that the one with biggest 0 will win. Okay, so this is what Laughlin constructed. And then, the question is, what filling factor does it correspond to? Okay, and you can calculate, so let me not do that, that this is 1 over 2m plus 1. Okay, and this is quite remarkable. Now let me tell you the story and stop here. So this is quite remarkable because the first plateau which was discovered was 1/3 filling factor. Okay, and then the story is from Laughlin's Nobel lectures, I guess. he was thinking about this wave function. He invented, and then he called, I think, Tsui, one of the experimentalists who discovered the whole effect. And he said that, okay, I know what's going on. And Tsui asked him, what's the next fraction? And Laughlin said 1/5. Okay? And Tsui said that almost. And actually, the next fraction was 2/5. And Laughlin waited for some time, and then Tsui said that there was some small thing at 1/5 indeed, and then he published that paper, which is like 4-page paper. But the 2/5 is the biggest plateau after 1/3. And from this point of view, it's not clear why. And this is my next story, if you want to hear it at some other point. But
should there be a different Laughlin wave function for 2/5?
There should be different function for 2/5. The function is pretty complicated. That's why I actually draw this two-field Landau level wave function just to modify it to make this one. But I don't have time for that.
Z bars in it?
Yes. No.
No.
It still should be from 1/1 Landau levels. Okay, let me. Remember, there was some Z1 bar Z1, this kind of thing in this determinant.
Yeah.
So the right way of doing this would be to write here Zi minus Zj squared product. Yeah. Okay, I minus smaller than j squared. And then here, instead of every Z1 bar, replace it by dZ1 in the determinant. Then you understand? So Z1 bar, Z bar comes from that exponent, but it's just, and then of course this factor, which is this. So this is a variational. This is good function for this 2/5 things. But it's very natural why this simple function with 1/5 has a smaller gap than this kind of huge and ugly. Well, not ugly. It's kind of beautiful. Remember that when I see that there is a good plateau at 2/5.
Yeah.
And there is smaller plateau at 1/5. My interpretation is that within this zeroth Landau level, if I fill it up to 2/5, there is some small energy gap formed, many body gap, between the ground state and the excited state. And the same with 1/5. The reason that this is robust and this is not robust, less robust, is that I believe that this energy gap is larger than this one. Okay. So you really have to understand why these plateaus of different size on the picture. You have to explain the hierarchy of gaps, which one is bigger, which one is smaller.
Before was that you have to go back to that many-body Schrödinger operator,
Right.
and try to understand gaps between its eigenvalues.
Correct. So the question is any kind of universal explanation of the hierarchy of gaps? And it turns out that there is a good argument why 2/5 is in some sense better than 1/5. This is called composite fermion construction, and then I can tell you.
Any kind of, but the gaps themselves, these widths, I mean, because they have to do with the hugely complicated spectrum of this many-body Schrödinger
Right.
operator, they don't have any simple formulas for these widths, do they?
No, for widths, no. I think they have some empiric formulas which are okay, but they have a lot of empirical formulas for little slopes of this plateaus for many things, but not of all of that explains. But the question is any kind of universal way to explain maybe not the size of the gap, but at least hierarchy, which gap is big, which one is small, which fractions you probably will see more than others, these things. And for this we have to talk about quasi-particles and composite fermion construction. Some other time. Okay.
Is this called?
Yeah, we should.
Okay. Let's this go. 2/3 as completely filled Landau levels with a third of electrons removed.
Yeah, it's a
Right.
vertical pull of 1/3.
Yeah.
And I would expect this to come before 2/5.
Oh no, 2/3 is strong too. 2/3 is too.
But it doesn't come before 2/5.
I don't remember. I mean,
Yeah, don't remember.
Is it? Well, 2/5 is not on this picture. No, there isn't. Oh yeah, 2/5 is bigger, right, on this picture at least.
Yeah.
But I'm not sure that it's right way to compare because its magnetic field becomes stronger by 2/5. So you really have to recalculate in energy scales. But
Actually, 1/3 is bigger than 1.
that's what I'm saying. That 1/3 is bigger than 1, but at 1/3 magnetic field is 3 times bigger. So h bar omega c is bigger. So what you really have to do is probably to estimate the ratio of this to h bar omega c. So basically, relative size is this divided by this. You have to compare. So it's a bit tricky, but 2/3.
One, okay, yes.
But 2/3, of course, are there. Right? The interesting point here, the one which is related to this composite fermion story, is actually filling 1/2. It's the only place where nothing happens. That turns out to be the most important for construction.
1/2.
1/2, because basically at 1/2 you have 2 flux quanta per electron. That's just, this is what 1/2 means, that you have 1 electron, 2 flux quanta.
That's that picture in that Stormer article of having these little fluxes.
But now I'm going to attach fluxes, right? So you're basically saying that if you take electron and take this whole magnetic field distributed uniformly and just collect it on each electron, 2 fluxes per each, then each electron sees on average uniform magnetic field, so this is sort of good approximation, one might think. So, but this object now is again fermion because it's 2 flux quanta interchange, the sign is the same, 2 flux quanta. But now it's free fermion because this guy moves with 2 flux quanta. This is non-interacting fermion, and so no other. So these composite particles do not feel external magnetic field, and they are fermions. So they form Fermi liquid with nice, good Fermi surface. Maybe this is very controversial stuff, but at least you kind of feel that there should not be a whole plateau, and this explains why this rho XX is not 0 anymore. It's dissipative. There is no gap at this point.
What's controversial? You think the
What exactly is the state of those composite fermions at 1/2?
Oh, yeah.
So there is Halpern Lee Reed paper which says that it's basically big Fermi surface of composite fermions.
Right.
But if you try to justify it and consider fluctuations, it's very badly controlled. So maybe it's more exotic than that. For example, Pfaffian state can be found because it's unstable. But again, that's another story. So, okay, I went through half of my introduction, so, but I tried not to rush. So,
Yeah, that's good.
okay.